So hello friends, this is Shubham Shinde and today we are going to see today we are starting with the third class of this lecture series on circular motion. So in this lecture series we will see the conical pendulum, the banking of the rod and many other topics. So we will start a new topic, that is the dynamics of circular motion. So I'll write the heading dynamics of circular motion. So what we'll learn in dynamics of circular motion is all applications wherein you will use the circular motion and its applications. So first we'll be starting with the banking of the rod. Okay. So starting with banking of the rod, why is banking required or what is banking? So in the countries where there is a lot of rainfall, or suppose when there is a rainy environment, the friction is not sufficient so that the car can take a turn. Like you are going on a bicycle and you are taking a turn. So you can see when the water is when there is a rainy season, there is water all over the road and your bike gets slipped and you get hurt. So this is because when the water falls on the road, the friction of the road decreases, and that friction can't provide you this considerable amount of centripetal force, and that's why you slip. So in order to prevent this slipping or skidding of the cars or on the vehicles on the road which are at very high speed, so to prevent those in these rainy conditions, the roads are banked. Okay, so what does banking of the roads ensure? The banking of the roads ensure that even if there is a rainfall, the bike or the cars can go at a speed without stopping or without even if there is no friction offered by the road. So this is why the banking of the road is essential, because it provides necessary centripetal force. Now we'll see how does banking of the road helps to provide the centripetal force. So while taking a turn, the centripetal force can be provided by either the friction or either by banking of roads. And in ideal condition, there will be no friction. Okay, but in day-to-day lives we have friction in the turning. Okay, so if we bank the road, now we will see banking of the road when there is no friction. Okay, that is an ideal condition. And in third condition we will see when there are both the components, friction as well as banking. Okay, so now we will see what happens when there is friction. Okay, and the car is taking a turn. So first point is friction present. Okay, friction only. The topic is banking of the roads, and first point in banking of the roads is the centripetal force is provided only by friction. So what will happen is, now suppose this is the car. Okay, this is the car. So now suppose this car is now taking a turn. Now remember, the centripetal force will always act towards the center. So if this is the center of the circular path, this will be the F centripetal force. Okay, so I'll denote it by FCP. So I know whenever a body is performing a circular motion, it has to have a centripetal force. But it's not decided in which condition which centripetal force. Means suppose I have tied a stone by a string and I am rotating that string. In that condition, the centripetal force is provided by the tension in the string. Now, when I am taking a turn on a road, I am performing a circular motion. And I know for performing a circular motion, I need a centripetal force. And in this condition, that centripetal force is provided by friction. So you can see, if I am doing a circular motion, obviously I am going to need a centripetal force. But it's not decided, or it's not always decided that which centripetal force will act where. Centripetal force can be anything. Like that, it can be tension when there is a string and stone, and here it can be friction. Means if I summarize, the centripetal force is a post, like president or a prime minister is a post, and this post is occupied by various different persons. Okay, so suppose if there is a person now, after 5 years there will be another person, but the post will remain the same. President will remain president. Likewise, the centripetal force is a post, and that post in different conditions is taken by different forces. Like I have told, tension in the string stone condition and the friction in this condition. Okay, so the centripetal force here is provided by the friction between the car and the road. Now we have to find out what is the next, what are the expressions, and how will we solve this. So here the centripetal force is provided by the friction. Now if I write it mathematically, I know FCP is equals to friction. Okay, and I know what is friction. Friction is given by mu n. Why I have taken mu n is because this is the maximum friction. Suppose the car is now going at a very high speed, that now this friction is also not useful. Then what will happen is the car will slip. Okay, so if the car goes at a very high speed, that even if this friction will not allow it to remain on the place, now it will skid. But if the car is going at a speed which will equate to force equals to this, then the car will not skid. So this is the boundary condition. If we equate this equal to the max friction and drive the vehicle at or up to that speed, our car will be safe, our car will not skid. But as we increase the speed beyond this velocity, our car is definitely going to skid. So we are finding that boundary velocity below which we are safe and above which it is dangerous. Now, so this friction is a max friction. So centripetal force is given by mv square by r is equals to mu. What is n? So this is a car. I know this is the n. What is n? N is equals to mg. So mv square. So can I write v is max? Because I have taken a maximum friction. Whenever this velocity or this friction will balance this or will allow the vehicle to run at the fastest speed, up till that point the car will run or car will not skid. But as the velocity increases a bit, the car will skid, because now the body can't give that, or body or the road can't offer that much friction. So I can call it Vmax by R is equals to mu mg. So if I cancel m on both sides, what am I going to get? I am going to get a formula where Vmax is equals to root over gr. Okay, so if you drive vehicle with speed equal to or less than root gr, your car is not going to skid, even if the road is banked or even if the road is not banked. But if you take the car at such a speed which is greater than this speed, that is root gr, your car is going to skid even if there is no banking and if there is friction. Okay, so I'll write Vmax which is less than or equals to root gr. So in this condition car is safe. But as Vmax goes greater than gr, your car is going to skid, because now I know I have taken the boundary condition. What max friction is allowed, I have taken it, above which I can't take or above which the road can't offer. Okay, so up till this point the road and the road friction can bear the vehicle, and above this speed the car will skid. So this is how we have seen what if the car or what if a car goes on a road which only has a friction and no banking. Now we'll see what if there is no friction and we only put only banking. So we'll see the next point. So what is banking first of all? So banking is now suppose this is a road. Okay, so this is a normal road, but I've told now I'll bank this road. What means banking? So I'll tilt one side or the outer side. This is the outer side road and this is the inner side of road. Okay, so I'll tilt or I'll push the outer side of the road little above, so that your road will, now this will be a new road. Okay, means in short, the outer side of the road or the outer edge of the road is tilted somewhat above or tilted little above the inner side. Okay, so that means the inner side is relatively at a lower position than the outer side or the outer edge. So this is the banking, and this will provide the necessary centripetal force and will prevent the cars on your bikes from skidding. So we'll see how. Now suppose this is a banked road, and now a car is going on this banked road. Now tell me, this will be what? This will be normal. Okay, what will be this? This will be mg. What will be this? And what will be this? So this is theta. So this will be n cos theta, and this will be n sin. So guys, now we'll see the banking only. Okay, so in the banking only, so I'll represent this diagrammatically. So suppose this is the banked road and this is the car. So this is the normal. I'll divide this normal into its two components. So suppose this is theta, which is the angle of banking. So when this is theta, so I can say that this is n sin theta, and I can say that this vertical component is n cos theta. Okay, and I know that mg is downwards. So now tell me, there are two components of n. One is the horizontal component and one is the vertical component. Tell me which is the component which will provide the centripetal force. As I have told earlier, centripetal force is a post. It's like a post. Okay, different persons at different time occupy it. Okay, so here in this condition, the n sin theta, the sine component or the horizontal component of the normal force, which you can see here, so this will provide the centripetal force in this case. In any other different case, there will be any other different force which will be providing the centripetal force. But in this case, n sin theta is the one which is providing the centripetal force. So I can say the centripetal force is equals to n sin theta. So I'll write it mathematically, mv square by r is equals to n sin theta. Okay. Now, see, the body is performing a circular motion in the x-axis. Okay, it is performing a circular motion in x-axis, as you can see here. But you can see that in the y-axis, so this is an x-axis. So when you'll see about y-axis, the body is at rest, or the car, vehicle, or your cycle is at rest. It is not going up, it is not going down. The body is at rest in the y-axis. And it will be only possible when upward force, that is n cos theta, will be equals to the downward force, that is mg. So I can write in y-axis the body is at rest. That means the two opposing force, upward force n cos theta, should be equals to downward force, that is mg. So we have these two equations. So what can we do with these two equations? So we'll now write an expression. So now if suppose I divide these two equations, what will I get? So n sin theta by n cos theta, n and n will get cancelled. So I'll get tan theta is equals to v square, m and m will get cancelled, v square by rg. Okay, so this is the formula which is very important and it will be needed in subsequent sections. So they will ask what is the angle of banking if the vehicle wants to go with some velocity v. The circular motion is done with a radius r and you know the value of g. So you can find out the value of theta. Sometimes they will tell you the width of the road is to be b. So what should be the height up till which the upper edge of the road shall be tilted? So I can say that tan theta is equals to opposite, that is h upon base. So this is equal. So in this way I have told you another numerical aspect of this question. How can you find height? Or they'll ask in the question up till what height shall be the road or the upper edge of the road tilted so that the angle of banking shall be this and that. So you can find this by this formula. Now we have seen banking only concept, but now we'll see when there is banking plus there is friction. Okay. So banking and friction. So I'll again represent it diagrammatically. So this is the banked road and this is the vehicle. N mg is downwards. Okay, so banking and friction is a very elaborate condition. Here I'll not get a single V, I'll get two V. One is V minimum and one is V maximum. Why do we get these two velocities in this case? So suppose to avoid any accident or to avoid any mishappening, suppose the car is going at a very low speed. So what will happen is that when the car is going with very low speed, it will go on decreasing, and at one point the speed will be such that it will skid towards the lower edge. Okay, so means there is a V minimum, or there is a minimum velocity below which we should not go, otherwise our car will skid to the lower side or towards the lower edge, okay, or towards the inner edge. And there is another one velocity above which if we go, the car will skid, okay, or car will be thrown out of the road towards the outer edge of the road or the higher edge of the road. Okay, so we have to find V minimum as well as V maximum. So here you don't get just one V, here you get a band of V between which you can drive the vehicle to be safe, to avoid any accident or any mishappening. If you go below V minimum, your car will skid towards the inner edge. Above V maximum, if you go, your car will skid towards the outer edge. So this is how you have to drive your vehicle between V minimum and V maximum. So this is the optimum band between which you can drive the vehicle when there is banking and when there is friction. Okay, now we'll see. So now when I'm talking, I want to find V minimum. Okay, so when can we find V minimum? Suppose the car is going and it is decreasing its speed gradually. So at some point you'll get a V below which the vehicle will skid, and that is the point you will get the V minimum. Means the car is going to skid downwards. So tell me, where is the friction going to act? The friction is always going to act opposite to motion, and if the car is going to skid downwards, the friction will act above. Okay, so this is the direction of friction. So friction is in this direction. Now I'll divide the normal force and friction into its components. So this is the angle theta, angle of banking. So this is the horizontal component, and this will be F cos theta. And this component of friction will be F sin theta. Okay. This component of N will be N sin theta, and the vertical component will be N cos theta. So now tell me again, in this condition, which force or which group of forces will contribute to the centripetal force? In this case, there will be not a single force which will contribute to the centripetal force, but in this, there will be two forces which will be contributing to the centripetal force. Those are the N sin theta and F cos theta. You will be confused that F cos theta is in the opposite direction to the centripetal force. Then how come is it contributing in the centripetal force? Please understand, even though the F cos theta is different in direction than N sin theta, but it will contribute in centripetal force because the centripetal force is a net of all forces. Okay, so N sin theta minus F cos theta is equals to mv square by r. N sin theta will be always greater than F cos theta. This has to happen because if N sin theta is not greater than F cos theta, then this will not be a circular motion. So this is our first equation. So this is in x-axis. The body is performing circular motion in x-axis. Now what will happen in y-axis? In y-axis, I know that the body is not moving down and the body is not moving up. Means the net of the upper forces, which is the N cos theta and F sin theta, shall be equals to the downward force, that is the mg. So N cos theta plus F sin theta is equals to mg. So N cos theta plus F sin theta is the net above force and mg is the net below force. So I know in y-axis the body is at rest. The body is not going up. The body is not going down. Means this can only happen when the upper acting forces is equals to the lower acting forces. So in this way we have got our second equation. So in this fashion we have got our two equations. Now we'll equate these two equations to arrive at the final formula. Okay. So now I'll divide these both equations. So I'll get n sine theta minus f. What is f? Friction. And what is its value? Its value is mu n cos theta is equals to mv square by r, which will be divided by the next expression n cos theta plus f. F is again mu n sine theta mg. So I know this n is constant everywhere, so this n will be cancelled out, and also the m is constant in both equations, so m will be cancelled out. So I'll get sine theta minus mu cos theta upon cos theta plus mu sine theta is equals to v square upon rg. So this is the simplified formula of this expression, which will be simplifying more. So now this can be simplified more if you know a formula from trigonometry. So this will be equate to, I'll rub this and write a new formula. So this will equate to tan theta minus mu upon 1 minus mu tan theta is equals to v square upon rg. So this is the most simplified formula obtained. So what is v square? So v square is tan theta minus mu upon 1 minus mu tan theta into rg. So in this way we can find out the value of v. Okay. So what is this? This is the v minimum. And suppose the square goes on this side, then this will be root. Okay. So in this way we have found out what is v minimum. Okay. Now we'll be finding out what is the expression of v maximum. But before that, I like to elaborate this formula even more. So suppose we had formula v minimum is equals to root of tan theta minus mu upon 1 plus 1 minus mu tan theta into rg. So I suppose that mu is any tan phi. Okay, so my expression will be v minimum is equals to tan theta minus phi dot rg root over. Okay, so this is the expression or the simplified expressions. Okay, and now I'll add some more points. So whenever the speed of the car is greater than this v minimum, the car is not going to skid. But if speed of the car is less than v minimum, the car is going to skid. So you can take equals to condition over here. So whenever the velocity or the speed of the car is greater than equals to the v minimum, it is not going to skid. But when it goes below v minimum, it is going to skid. So in this way we have understood what is the v minimum. Now we'll be going to the next topic or the next part, that is the v maximum. Okay, so what is v maximum? V maximum means I am driving a car, okay, or anybody is driving a car, and that person goes on increasing the speed, At one point, the speed will be so much that the car will not be able to cope with the centrifugal force, and it will be thrown outwards of the road towards the outer edge. So to prevent this, I have to drive the car below the V maximum. Okay, if I exceed the speed above V maximum, the car is going to skid. Okay, so I'll draw a figure. So I know that this is a normal again. Now tell me, when I'm driving at the maximum velocity, there's a tendency that the car will skid outwards or towards the outer edge. Hence, the friction will act towards the inner edge, because the friction, I know, always acts opposite to the motion. And motion in this case is towards the outer edge. So the friction is going to act towards the inner edge. So this is the direction of friction. Now, I'll again divide the normal and the friction force into two components. So this one component and this is the another component for friction. So this is going to be F cos theta and this is going to be F sin theta. For normal, this is going to be n sin theta and this is going to be n cos theta. Okay. Now we have just divided these components. Now we'll write the equations. So I know in this condition, in the previous condition, those all who were lying along the x-axis were contributing into the centripetal force, and both were in the opposite direction. So there was a subtraction. But here you can see, here both the components of the normal force and the frictional force are acting in the same directions, and hence they are culminating in an addition and they are contributing in an even greater magnitude as compared to the initial V minimum concept. So here I can say that the centripetal force is addition of n sin theta plus F cos theta is equals to mv square by r. So this is my first equation. Now I know in y-axis the car is at rest, or car is not going up or car is not going down. This can only happen when the upward acting force is equals to the lower acting forces. First equation, where n sin theta plus F cos theta is equals to the net centripetal force, which is equals to mv square by r. Now I'll see the y-axis. I know in the y-axis the above acting force should be equals to the below acting force, so that the body is at rest in the y-axis. And the thing is, yes, the body is in y-axis. Seen the n sin theta plus F cos theta is equals to the net centripetal force, which is equals to mv square by r. Now we'll go into the next expression. In y-axis you can see this body is at rest, and it can only be at rest when the above acting force is equals to the below acting force. So what is the above acting force? It is the n cos theta is equals to what is the below acting force? It is mg plus F sin theta. So this is the second expression which I have got through this diagram. Now I'll rub this diagram and now I'll calculate or solve these two expressions simultaneously. So if I divide these two expressions, I'll get n sin theta plus F cos theta is equals to mv square by r upon. So I can write this as mu n. Here I can write n cos theta minus mu n sin theta is equals to mg. So in this way I have written these formulas. So I can see n is constant. I'll cancel n. M is constant. I can cancel m. So it is sin theta plus mu cos theta upon cos theta minus mu sin theta is equals to v square by rg. So this is the expression which I have got up till now in a simplified form. Now I'll simplify it more. So using the trigonometric equations, I can write it as tan theta minus mu, tan theta plus mu upon 1 plus 1 minus mu tan theta. Dot is equals to V square by Rg. So up till now, this is the most simplified formula which you have got. So you can write, so this is Vmax, okay. So Vmax is equals to tan theta plus mu upon 1 minus mu tan theta dot Rg. So if this comes in root. So this is the ultimate expression of Vmax. Okay, so you should not drive your vehicle above this Vmax. If you drive, your car or your vehicle or your bike will skid, your cycle will skid. But if you drive your vehicle, your bike, your car or your cycle below this velocity, you will be safe. Okay. So now, if mu is equals to tan phi, so I can write my formula is Vmax is equals to root over tan theta plus tan phi upon 1 minus mu tan phi dot Rg. So it can be written as root over tan theta plus phi dot Rg. So this is the most simplified formula you can get for the Vmax. So this is essential when you are solving numericals where they express mu in the terms of tan theta. Okay, so this is the very simple expression which you can remember for your subsequent questions. Okay. So in this way we have completed all the problems or all the concepts which will be required for banking of the road and applied concepts. Now we will see the next concept, which is the conical pendulum. Okay. So conical pendulum. How is conical pendulum different from a simple pendulum? I know simple pendulum performs a motion to and fro. So this is a two-dimensional motion in which the ball moves in an x-axis and a y-axis. But conical pendulum is the one which moves in x-axis and z-axis. This is also a two-dimensional, but the trajectory it makes just circumscribes a cone. Like when this is a simple pendulum. Okay, so it performs a to and fro motion, but this pendulum is not going to go in a to and fro motion. This will go in a circular motion. Like if this is a ball, then this will be allowed to rotate or move in a circular manner. So tracing the trajectory of this ball, you can see this ball will circumscribe or traverse a circle, and the resultant trajectory or the resultant shape formed by this string, this particle and its circumscribed path will make a cone. That's why this pendulum is called as a conical pendulum. Understand? So in this way I have told you why is it called a conical pendulum. Now we will see what are the kinematics and dynamics of this conical pendulum. So suppose this is the roof and you have tied a ball to this roof, and the ball, suppose at some point is at this position, at some point it will be at this position, and between these positions it will perform a circle. Okay, so in this circular pattern it is going to move. So you can see that the center of the circle is here O, and this is the circle in which it is going to move. Here there is a tension because it is a string. The mg will be directed downwards. Okay, so now I'll divide this tension into two components. One is the horizontal component and one is the vertical component. So First, I shall denote a theta. So this is a theta. So you can see here, this will be 90 minus theta. So it will be t cos, sorry, it will be t sine theta. And it will be t cos theta. In this condition, tell me which is the force which is providing the centripetal force. In this case, the centripetal force is provided by a special force which is tension and its component T sine theta. So T sine theta is the force which is providing the centripetal force. So I can write T sine theta is equals to mv square upon r. Okay. Now I know that the ball. So in the simple pendulum, I know that the ball was also going up and going down. So I cannot say in that condition the ball is at rest in y-axis. But in this condition, I can say that the ball is in rest in y-axis. That's why I can say it only when the above acting forces is equals to the lower acting forces, which is mg. So I can write above acting forces t cos theta is equals to below acting forces mg. Okay, so in this way we have just collected all the information from this diagram, and now we'll equate these two equations to write a new simplified equation. So if I divide both these equations, t and t will get cancelled and I will get. So guys, now we have these two equations, one in the x-axis and one in the y-axis. Okay, so now we are going to equate these two equations and we are going to find out the new simplified equation. Okay, so if I divide these two terms, so this is the first equation and this is the second equation. If I divide these two equations, what will I get is t and t will get cancelled. So the expression is tan theta. The expression will be tan theta is equals to v square, m and m get cancelled by rg. So this is the simplified formula. Okay, so this is the formula which will be used in the case of conical pendulum. Okay, and you will find it similar to the one which we have seen, to the formula which we have seen in the banking of the roads. Okay, so the formula are somewhat similar. So but understand one point, that this is the radius. Okay, this is the circle in which it is going to perform a circular motion. Sometimes it is some students find it confusing that which is the circle in which the particle is performing circular motion. So this is the circle which is in the xy plane. Okay, sorry, it is in the xz plane. Okay, and this is the length of the string. So sometimes what they give is they give the length of the string. Okay, so if I draw the diagram, this is the length of the string, this is the radius, and this is theta. So the equation which you can get is cos theta is equals to r by l. So you can use sometimes this in this formula to find out the answer if you are asked so. Okay, so in this way we have completed the conical pendulum. Now we will be going to another concept, which is, we'll see, okay, so that concept is called as death well. Okay, so what happens in death well, this is a structure. Okay, so it is a drum like structure. Okay, it is a drum like structure, and some stuntmen who ride bicycle come and try to rotate or try to move or try to traverse or try to pass through this death well, okay, without even touching the floor. They ride their motorcycle not on the floor but on the wall. Okay, so what is the concept here which pertains or which is okay, so how means can we relate circular motion to this topic? So thus suppose this is the motorcycle. Okay, so I have drawn it with a circle. Okay, so in this case understand where is the normal force acting. Normal force I know is always perpendicular to the surface. So surface is this. Okay, so perpendicular to the surface will be in this direction, normal. And tell me which is the, or what is the path, or where is the circular path. So the circular path is this. Okay, so the body is going to rotate, or the stuntman is going to rotate in this direction or in this path. So in this case, if I ask you where or which force is going to act or contribute to the centripetal force, okay, in this case this normal force is going to contribute to the centripetal force, that is N is equals to mv square by r. Okay, sometimes you may feel that how can this normal act as a centripetal force, but here the case is such that the normal act as centripetal force because the motorcyclists or the stuntmen perform or drive their motorcycles or drive their bikes not on the ground but on the walls. Okay, so this is the point, this is the center, and the centripetal force is provided by the normal force in this case. In this way we have understood what is the death well. Okay, so sometimes they ask, sometimes there is a concept that suppose there is a friction. So now tell me, so when they are performing the stunts, there is a chance so that they can fall down, okay, or they can slip. So they have a chance to slip downwards. Hence, their tendency of friction is to act above or in the upper direction. Okay, so up till boundary condition, up till suppose friction is is considerable amount. Okay, it is in good amount. So they will overcome mg, and the stunt person will not fall. But at a boundary condition, if suppose the friction is less, then this mg can overcome this friction and the person may fall. So at up till boundary condition, mg is equals to friction, and I know friction is equals to mu n, and I know what is n. N is mu m v square by r. So if I cancel this m and m, what will I get? I will get g is equals to mu v square by r. So I'll get v as v is equals to gr by mu. So this is the equation where you can find the velocity with which the motorcyclist or the stuntman is performing the stunts. Okay, so this is very important formula which will be used in solving the problems of death well. Okay, so in this way we have completed the concepts of dynamics of circular motion, where we have applied the concepts of circular motion which you have learned in kinematics. Now we'll be going on to the next concept, which is the whenever we rotate any body in the vertical circle. Suppose I have tied a stone to the string, and I'm just rotating it in the circle, okay, in the vertical circle. So that is the special case of circular motion. Okay, so in that condition we will learn in the next class. Okay, so this is it for this today's class. I hope that you enjoyed today's class. If you have any doubts, please feel free to share.